everyone, we're starting off Unit 1, Section 2 with matter. So you'll need for today notes, which are just pen and paper. So here's an overview. We're going to talk about what matter actually is and what it isn't, and the two different types of matter. There are pure substances, which are elements and compounds, and mixtures, which are homogeneous mixtures and heterogeneous mixtures. We'll also have a separate video on separating those mixtures. So pretty much what is matter? It's anything that has mass and takes up space, which is volume. It can be a solid, liquid, gas, or an aqueous, and it's made up of pure substances and mixtures. Things that aren't matter are shadows, any type of energy, so we have thermal energy, electric, light, kinetic, potential, and wind. There's a whole bunch of things that aren't matter, but these are just some examples for you. So again, matter is anything that has mass and takes up any space. So we have a flow chart that we're going to form here. So go ahead and draw it with me. You'll need, I usually do about maybe 10 lines worth or spaces worth, but you can just do this as a draft if you need to. So when we look at matter, we look at its type of composition. We have two different types. One is fixed composition. So for fixed composition, we call them pure substances. And fixed composition is anything that is always going to be the same ratio of different elements. So from there, we talk about if these substances can be separated chemically. If they cannot be separated chemically, we'll call them elements. And if they can be separated chemically, we'll call them compounds. So here are two particle diagrams. One's of an element, the other's of a compound. So for the elements, you'll notice that they have just one type of substance there. There's not anything else. There's only just black dots here. In the compounds, we have black and white dots combined together, and they're physically together. So we call them compounds. So those are fixed compositions for pure substances. If they have variable composition, meaning not fixed or the composition itself can change up a bit, we call them mixtures. And then we talk about if they're uniform throughout, meaning do they look the same throughout the container. If they don't look the same, we call them heterogeneous. And here's a particle diagram for there. So you'll notice with the heterogeneous particle diagram, we have two different types of compounds. Actually, the compounds down at the bottom, and we have white dots that are together, which are elements, and they're separated, meaning that the white dots are at the top and the black and white dots are down at the bottom. If they are uniform throughout, meaning they look the same all throughout, we call them homogeneous. So here we have the black dots together and the white dots, and they're just kind of mixed all throughout. So make sure you get down this flow chart. So for pure substances, the two different types are elements and compounds, and they cannot be physically separated. They have fixed composition, meaning they're always going to be the same ratios, and they can be solids, liquids, and gases. So the first type of pure substance that we talked about was elements. These cannot be broken down by chemical means. You'll also see cannot be chemically decomposed. So these are just two phrases that you might want to cue in on when you're looking at any multiple choice questions. So any elements cannot be broken down by chemical means or cannot be chemically decomposed. They're represented by symbols, and you've seen these symbols before. They're 1 to 3 letters, and the first letter is capitalized. So helium, for example, is going to be He. Hydrogen is going to be H. Oxygen's O. And these are found in the periodic table and table S. So some examples of things that are considered elements but are kind of out of the norm are those diatomic elements. We call them Hunkelbriefs. So it's hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. So recall that diatomic elements are just elements that are together when they're not combined with any other element. And these are just going to be these 7 elements that are going to be together when they're not combined with any other elements. So here's an example of iodine. It's actually undergoing something called sublimation, which is going from a solid to a gas. So it's a purple substance. And here's just a reminder of what the particle diagram looked like for elements. And here's another example. The one on the right is actually showing you a particle diagram for any of these diatomic elements. So you'll see that this could be H2. So the 2 little white dots are each representing an H, and there's, of course, 2 dots in them. The second type, or the other type of pure substance, are compounds, and these can be broken down by chemical means. You also see these other 2 phrases. They can be chemically decomposed or chemically separated. So make sure you underline and highlight those in your notes just to make sure that if you see a multiple choice, you can cue in on these. And they're separated by something called electrolysis. And we'll go into that a little bit later, but again, this is a simple little multiple choice thing. It's kind of recalling, okay, electrolysis, it should be dealing with compounds. They're made up of two or more different elements. Make sure we keep in mind different elements. The Hunkelbrist, so those diatomics, were just elements. So H2 is just two hydrogens. They're two of the same elements, whereas compounds are two or more of different elements. And the common compounds to know are ammonia, which is NH3, it's usually a gas, water, H2O, when you saw liquid or gas, and this is the particle diagram. Recall from back in bio that water kind of looks like a Mickey Mouse shape. It's a bent structure with the oxygen in the middle, and the two hydrogens are Mickey Mouse's ears. The other type of compound to know is methane, which is CH4, and that's usually a gas. So those are pure substances, or just substances. These are going to be mixtures. So there are two types of mixtures, heterogeneous and homogeneous. And these can be physically separated. So again, there's a separate video on how to separate out mixtures, and those are all physical separations. They're not a fixed compound, so you could have, an example of this would be salt water. So you could have salt and water, but the ratio of salt and water can be different from one sample to another sample. So if I asked you, or each member in your group, to make salt water, you could each put in a different amount of salt to water, and that would be a mixture. We have solids, liquids, gases, and aqueous solutions. So the first type of mixture we'll talk about are homogeneous, and we have the particle diagram below. So if you notice in the particle diagram, we actually have a molecule here, or excuse me, a compound here. This could be water, H2O, and we have a separate or a different compound there. This is going to be a mixture because there's two different types of compounds here. Alright, sorry for that pause, guys. Alright. Okay. Particles are evenly distributed, meaning that they're uniform all throughout. You can't see any physical separation. Some examples are air. Air is made up of nitrogen, oxygen, water vapor, and other gases. We have tap water. Any water that we take out of our sinks at school will have water as well as separate ions in there. That's why we use distilled water for many of our experiments, because distilled water just has pure H2O. It should not have any other ions in there. Tea is an example. Brass, and actually I showed you a picture of brass right down here for you. We made brass a few weeks ago, or when we talked about the gold penny. So here we had the copper penny, we coated it with zinc, and then we heated it. When we heated it, the copper and the zinc combined together to form brass, which made it look like gold. Sorry guys, it's not actually gold. And another example of homogeneous mixtures are aqueous solutions. We call them miscible. Miscible just means that they'll dissolve in one another. And solutions. So solutions are major homogeneous mixtures. And there's two different parts of solutions. One's the solute and the other is the solvent. So the solute is dissolved into the solvent, and the solvent dissolves the solute. So pretty much whichever one is in less amount, we do call that the solute. The greater amount is the solvent. And water is something called a universal solvent, meaning it can dissolve a lot of things. And that's due to its polarity, which we'll learn about in Unit 2. So here's just a quick multiple choice question. Which sample represents a homogeneous mixture? So for homogeneous mixture, we want to find something that has more than one compound in there. So for A, we have C2H5OH. That is just one compound, and it's a liquid. In fact, if you look at all of these, we have A, B, C, and D, they're all the same compound, C2H5OH. So here you have to cue in on the states of matter. We have liquid, aqueous, gas, and solid. So liquids, gases, and solids are just going to be the same composition, whereas aqueous, we actually add in water to make it an aqueous solution. So really, this is going to be C2H5OH and water combined to make the aqueous solution. So that's why B is a homogeneous mixture. The rest are going to be compounds. So here are heterogeneous mixtures. We have two examples here. Oil and water is one example, and then on the right we have soil, or it could be sand. So on the left, the oil and water, we have the oil is the yellow substance. It's not going to be dissolved fully in the water. It's heterogeneous, so you can actually see the separation between the two. Same thing with the soil on the right-hand side, or that sand. We have different layers when it's mixed in with water, and usually the layers form when it has a different density. So heterogeneous mixtures, the particles are not evenly distributed. So our particles here in oil and water are, of course, the oil and the water. So we have water like in there, oil over here. They're not actually combined together. Here with the soil, we have different layers of soil. Here's one layer, here's another, there's even some more above there, and then here's some water as well. So we have 3 distinct layers. So examples are sugar that hasn't fully dissolved in water, or your lemonade. So if you have a glass of lemonade, or lemonade, the sugar won't fully dissolve. You'll have sugar particles down at the bottom. That is a heterogeneous mixture. Oil and water is an example, and sand and water are examples as well. We call this immiscible, meaning that they won't dissolve in one another. So for some review questions, which type of matter is composed of 2 or more different elements that are chemically combined in a definite ratio? So I'm going to use my highlighter. I'm going to highlight some important facts here. We have 2 or more and chemically combined, and we want a definite ratio. So look back at your flowchart. When we have a definite ratio or for fixed proportion, we're talking about substances. So substances, or pure substances, would be an element or a compound. Here we have 2 or more different elements, so we'll call that B, a compound. For the next question, the list below shows 4 samples, A, B, C, and D. Which samples are substances? So again, these are talking about the pure substances. On our flowchart, this is the left-hand side. It's dealing with elements and compounds. So we want to make sure we find something that's not going to be a mixture. Like we saw in a previous example, anytime we have aqueous, we actually know that we're adding water to them. So I'm just going to make sure I show that when you have aqueous, it's adding H2O. So A and B are each aqueous. It's HCl and water, and B is NaCl and water, salt and water. So C and D are the only substances that are actually going to be pure substances, not mixtures. So D is our answer here. Which terms are used to identify pure substances? So we have to think back to our flowchart. Which section are pure substances? And if you looked back at your flowchart, take a look at it. You'll see the left-hand side, those are going to be B, elements and compounds. The next question, which 2 substances cannot be broken down by chemical changes? So we want to make sure that we see something that cannot be decomposed by chemical means. So go back through your notes, check to see which ones they are. Pause me if you need to. So now that we'll see it's actually B, C and Cu, because C is carbon, Cu is going to be copper. Those are each going to be elements. Everything else here, for A, C is an element, but CuO is a compound. For C, CO2 and CuO are each going to be compounds. And for D, CO2 is a compound, Cu is an element. The next question, which sample of matter is a single substance, meaning it doesn't have anything else mixed in there? So when we look at these questions, we want to see which ones are not going to be mixtures. We know that air is actually a mixture because it's composed of nitrogen, oxygen, water vapor, methane, etc. B, ammonia gas. So this is one of the ones I had you remember. It's just going to be NH3. And it's a gas. It's not combined with water. So this is going to be a compound. Let's take a look at the others. C, hydrochloric acid. So this is HCl. And we haven't quite looked at this yet, but if you see anything with an acid, it's added in with water. And then D, salt water. So here you could have NaCl and H2O. So the only thing that's a single substance is B, ammonia gas. 2 solid samples each contain sulfur, oxygen, and sodium only. These samples have the same color, melting point, density, and reaction with an aqueous barium chloride solution. It can be concluded that the 2 samples are the same. There's a lot of stuff here, and we haven't talked about the color, melting point, density, and reaction. But if you recall, we can know that melting point, density, those are distinct for elements and compounds. They have to have a fixed ratio in order to be an element or a compound. And they each contain sulfur, oxygen, and sodium. So we know that there's sulfur, oxygen, and sodium in there, so it can't just be an element because there's more than one element there. We have the same melting point and density, so we know that it can be actually a compound. The next question, every water molecule has 2 hydrogen atoms bonded to 1 oxygen atom. This fact supports the concept that elements in a compound are. So here we have to know what the definition of a compound is. So for compounds, we know that they are going to be they're going to be chemically combined and in a fixed proportion. So A is our answer here. Which substance cannot be broken down by chemical change? Meaning, so if we have something that's not chemically decomposed, cannot be broken down by chemical change, go back to your notes and find out which one it should be. And we know it's a substance, so it should be an element or compound. And since it cannot be broken down by chemical change, we know it's going to be an element. So here we have to look at all of these to figure out which ones are elements. This is why I had you make sure you remembered what methane was. That's CH4. That's going to be a compound. So A can't be it. We have D over here. That's water. H2O. That's going to be a compound as well because it's 2 different elements. Now we're down to B and C, propanol and tungsten. So here, take a look at table S. Find out which one's on there. If it's on table S, it's going to be an element, so that's going to be our answer. And in this case, C is our answer, tungsten, which has a symbol of W. When sugar is dissolved in water, the resulting solution is classified as. Alright, so we know that we have sugar and water. It's being dissolved. We can assume it's being fully dissolved as well. So if it's being fully dissolved, it's going to be uniform all throughout. Let's take a look at our answer choices. Let's try to get rid of anything that's trying to skew us or make us confused. If you notice, C and D, C is a homogeneous compound and D is a heterogeneous compound. These 2 terms will not be connected with one another here. So we're going to get rid of C and D because homogeneous and heterogeneous just refer to mixtures. So now we want to know which one is going to be this sugar or water. So if it's fully dissolved, it will be A, homogeneous mixtures. Which statement describes KCl, aqueous? Okay, so cue in on that aqueous or AQ. And we know it's going to be KCl and water. Right. So now we need to go back to the terms from before. We know it's aqueous, so it's going to be a homogeneous mixture. It's going to be uniform all throughout. So if it's homogeneous, we'll get rid of B and D. And now we need to know if KCl is a solute or a solvent. Now we said that the solute dissolves in the solvent, and water is usually as the universal solvent. So we know that water will be the solvent. That leaves KCl to be the solute. So now we're down to A. KCl is the solute in a homogeneous mixture. Alright, so here we have some particle diagrams. Which diagram represents a mixture? So we have particle Z is the filled in dot. Particle X is the filled in dot. Particle Z is the just the circle. So we want to find a mixture between the 2. It doesn't say heterogeneous or homogeneous, so that's fine. We just want something that has both X and Z in there. Now A has X and Z, but they're actually going to be combined together. That's a compound. It's chemically combined. It's going to be next to one another or attached to one another. C just has particle Z. It doesn't have anything of particle X, so we can get rid of that. Same thing with D. D is going to be just particle X, nothing of particle Z, so we can get rid of that. C and D are each going to be elements. So B is our choice. We have both particle X and particle Z, and they're not chemically combined. Alright, the next question, given the diagrams X, Y, and Z below, which diagram or diagrams represents a mixture of elements A and B? So we see here that A is going to be the open dot, B is going to be the filled in dot, and we want to have a mixture of the elements. So they're going to stay as elements. We're not going to chemically combine them. We're not going to form compounds. So let's take a look at sample X. Sample X has both A and B, but they are chemically combined. So those are going to be compounds, not mixtures. Y just has element A, nothing of element B, and that is just going to be an element. This is just one of the sample. So we have sample Z, So Z has both A's and B's, and they're not chemically combined. They're together next to each other, but they're not physically combined with one another. So Z is our only choice. Alright, so for a quick summary, matter has mass and takes up some space. It can be divided up into pure substances and mixtures. And pure substances consist of elements and compounds, and mixtures are homogeneous and heterogeneous mixtures. Can be homogeneous and heterogeneous. So make sure you take a look at the next video. It's on ways to separate out mixtures. Hope you guys have a great day. Take care.